Ubal. Good morning. My name is Ubal John. Before I get started, I'd like to ask you a question. Has anyone here ever experienced or heard of a disaster where a building collapsed led to casualties? You can raise the hands. Yeah, I see a few hands. So as for me, there was a high school gymnasium in my hometown that collapsed, and many students around my age lost their lives because rescue efforts are not timely enough. And this experience made me realize how important the efficiency is in disaster rescue operations. So as Professor Beisha highlights in the urban search and rescue field, the chances of saving trapped individuals are highest within the first 48 hours post-disaster. However, as Dunker and other researchers point out, rescue efforts in dangerous environments can put human rescuers at a significant risk. And this is where search and rescue robots come in as a promising solution. And that brings to my research project, developing a multi-target search and rescue robot based on improved algorithms. Search and rescue robots have gained significant attention in recent years for their potential to improve disaster response. And one thing that really caught my attention was how inefficient the path planning algorithm became in environments with multiple target points. So I came up with my initial research question. How can the efficiency and effectiveness of path planning in multi-target search and rescue robots operating in complex environments be improved? So with that question in mind, after reviewing a range of papers, I found that first, traditional path planning algorithms have their limitations. One example is Dijkstra algorithm, introduced by E.W. Dijkstra. It performs well in static environments. However, in dynamic rescue scenarios, Dijkstra's methods struggles to keep up with the sudden environmental changes. So given the limitations, researchers started seeking more efficient alternatives. One such solution is the A-star algorithm proposed by Hart and Nelson, which incorporates a heuristic function to estimate the cost to the target, thus enhancing computational efficiency. And this makes A-star better than Dijkstra's algorithm in complex settings. Yet A-star struggles with managing multiple targets effectively during search and rescue operations. So to address this, John and Zhao combined A-star with the Dijkstra's approach in their research on multi-robot rescue scenarios, significantly boosting the search efficiency. And this study shows that integrating traditional path planning algorithms is an important and feasible way to improve path planning algorithm. And it became the exact method I later used to develop the improved algorithm. Beyond optimizing path planning, the advent of simultaneous localization and mapping, which is called SLAM, has dramatically increased the effectiveness of search and rescue robots. SLAM allows robots to build maps and locate themselves in unknown environments, which is a crucial advantage in disaster scenarios where pre-existing maps are not often available. Research by Grassetti and Quassetti demonstrated that integrating SLAM with the A-star algorithm greatly enhances a robot's ability to adapt to its surroundings, ensuring efficient operation in dynamic environments. So introducing SLAM technology into my research project enabled the robot to perform mapping and path planning in the experiments, which greatly ensured the smooth progress of the experiments and reliable data collection. In addition to path planning and localization, managing target priorities is another key factor affecting rescue efficiency. Researchers like Chu and Colossi introduced the target prioritization in the development of their search and rescue robots, which allowed the system to achieve the practical significance, such as rescuing injured individuals first. And these studies emphasize that target priority management is essential for optimizing search and rescue robots. And this gives me the idea to consider the target priorities when developing the algorithm later on. So even though existing path planning algorithms have been optimized in many studies, there are still key research gaps in multi-target environments. First, one of the biggest challenges for the traditional path planning methods is their lack of real-time adaptability, and the current research hasn't yet improved this aspect enough. Second, while multi-target path planning has made some progress, There's still a gap when it comes to balancing route efficiency and with the rescue priorities. Additionally, although the genetic algorithms have been widely explored for complex optimization problems, like the traveling salesman problem, which is called TSP, their practical application in highly dynamic environments remains quite limited. So as my research deepened, my focus shifted from just boosting the efficiency and effectiveness of the traditional path planning algorithms to optimizing them for real-time adaptability and target prioritization. So my revised research question is, how can the traditional path planning algorithms be improved and integrated to optimize real-time adaptability and target prioritization in multi-target search and rescue missions? So based on the analysis of existing literature, I propose two hypotheses. First, integrating A-star, Dijkstra, and TSP algorithms can significantly enhance the path planning efficiency and real-time adaptability of search and rescue robots in multi-target missions. Second, in developing of path planning algorithms compared to using a single A-star or Dijkstra algorithm, a TSP-integrated path planning approach is likely to perform more efficiently in multi-target rescue missions. So in the field of search and rescue robotics, evaluating the effectiveness of various algorithms usually involves a mix of simulation tests and physical experiments. For instance, dynamic environment simulations are conducted using the platforms like the robot operating system, which is called ROS, to create realistic rescue scenarios. And in these simulations, robots autonomously navigate the complex terrains, avoid obstacles, and search for multiple targets. And one example is James' work, where his algorithm was tested in a multi-target simulated environment, proving that a simulation test can optimize multiple path planning objectives at once. And on the other hand, physical testing plays a crucial role in validating the real-world effectiveness of these algorithms. Kenny and Ken, for example, developed a search and rescue robot prototype and evaluated in actual environments to assess some key capabilities of the robots. And this combination of the simulation and the physical testing ensures a comprehensive evaluation of both the theoretical and the practical aspects of the robotic systems. So based on the analysis of the common methods in this field, my modified research method consists of three phases: algorithm design and development, robot design and integration, and experimental testing and evaluation. First, during the algorithm development stage, I chose to combine A-star, Dijkstra, and TSP algorithms to develop the improved algorithm. And this picture shows the flowchart I used to design the improved algorithm. Then I conducted the simulation test to compare the performance of this improved algorithm with the traditional ones. And next, in the robot building stage, I carefully selected appropriate sensors and hardware to build an experimental robot, ensuring that the upcoming physical experiments can run smoothly. And this image shows my design diagram for the hardware connections of the robot. And finally, in the physical experimental stage, I plan to conduct the maze experiment in an empty 10 by 8 meter cluster. I used the foam boards to construct the physical maze, and the robot would enter the maze twice. The first time, it would explore the empty maze to test its environmental perception and map construction abilities. And the second time, the robot would re-enter the maze with the target points added, testing its path planning and target execution performance. So after finishing all the experiments, I completed a detailed data analysis. In the simulation-based testing, I conducted virtual mazes in the ROS2 environment to compare 4 algorithms: Dijkstra, A-star, Dijkstra plus TSP, and A-star plus TSP in the different numbers of targets. So first, I compared their path planning diagrams. With just one target, algorithms produced the similar direct paths. As the number of targets increased, the paths became much more complex. Moreover, both Dijkstra plus TSP and A-star plus TSP showed greatly improvements by minimizing unnecessary detours. And they provided a better sequence of visits, reducing the redundant travel. Then I focused on 2 key metrics: path cost and time cost. In the path cost comparison result, we can see that with 1 to 2 target points, algorithms achieve a similar path cost. At 4 to 8 target points, the path cost for the Dijkstra and the A-star increases significantly, while Dijkstra plus TSP and A-star plus TSP remain around 1,200. For 8 target points, the integrated algorithm achieved nearly a 60% reduction compared to traditional algorithms. In the time cost comparison, we can see that for 1 to 2 target points, A-star had the shortest computational time, and with TSP optimization adding a slightly overhead. At 4 to 8 target points, Dijkstra and A-star's computational time significantly increased, while Dijkstra plus TSP and A-star plus TSP maintained lower levels. So according to simulation results, A-star plus TSP achieves the best path optimization due to its path and time cost results. And moving on, in the physical test, I aim to verify the effectiveness of the A-star plus TSP algorithm in real-world conditions. So first, I successfully completed the robot's construction, as you can see in the pictures. The following tests showed that this setup allowed the robot to explore and navigate the maze effectively. At the beginning, the robot used the LiDAR to scan the empty maze and create an initial 2D map. And this proved that the SLAM system have the good accuracy and stability in real-world mapping. And after the robot completed the path planning based on the task, I compared its path planning diagrams in 2, 4, 6, 8 targets. With 2 to 4 target points, the passes were short, allowing the robot to complete the task quickly. With the 6 to 8 target points, the path coverage expanded, but the robot was still able to prioritize and complete all targets efficiently. And in its path and time comparison result, we can still see that it shows a data trend that tends to flat. And this proves that the physical test confirmed that the findings from the simulations, which is A-star plus TSP not only optimizes path planning, but also dynamically adapts to real-world environments. So in this project, I tested the A-star combined with TSP algorithm through both simulations and physical experiments. And this video shows one test sample for the robot doing the mapping and the path planning process. The results show this improved algorithm significantly reduces the path cost and improves efficiency in multi-target search and rescue missions. It is worth noting that when target points were fewer, TSP increased the computational time, which limits its use in simpler scenarios. But however, in the multi-target scenarios, the experimental results still largely confirmed my earlier hypothesis. And that said, my research had limitations. So the physical experiments were affected by the real-world factors like ground friction and the uncertainties in path moving. And additionally, my physical maze test environment lacks the complexity of the actual disaster sites, which means the algorithm's performance in more complex environments still need further testing. Moreover, my study only focused on one single robot. However, multi-robot collaboration is crucial in the search and rescue robot research. Coase and Murphy's research shows how collaboration can increase the flexibility in real missions, and this is a promising direction for future development. This study successfully developed and tested a search and rescue robot of systems using an improved algorithm. The combination of A-star and TSP proved effective in complex environments, reducing computational costs while maintaining the path-finding efficiency. Both simulations and physical tests confirmed the practical feasibility of this system. The implications of this project are significant. In real-world rescue missions, where time is crucial, robots using this method can quickly locate the targets and reduce casualties. And this research not only advances single robot systems, but lays the groundwork for intelligent collaborative rescue solutions. So looking ahead, this robot system can be improved by enhancing SLAM technology to boost environmental mapping accuracy. It is definitely another improving direction to expand into a multi-robot cooperation for smarter task allocation and data fusion. And finally, by integrating AI and machine learning, robots could adapt to changing environments more effectively, making the autonomous rescue missions faster and more reliable. They are my resources. Thank you.
Okay, sorry if I mispronounce anything, but you said, and based off your charts earlier, the A-star and the Dijkstra were better for single target missions. Do you plan to advance your algorithms to like try and match single target missions, or do you just want to focus on multiple target?
So yeah, so like more in the reality, there's more scenarios like there are like multiple targets, like multiple rescuing target points, and the goal of this project is to improve the efficiency of path planning robots in the multi-target scenarios. And as you mentioned, the A-star and Dijkstra algorithms are traditional path planning algorithms in the field, and they are more focusing on the like one single target path planning. So my goal was to try to integrating the traditional path planning algorithms to improve the efficiency in the multi-target rescue operations.
Hi, Yubo.
Hi.
If you're looking forward, are you looking forward to keep like to improve like this project? And if you do, like what you will change on it, or what improvements you will do?
Sorry, I didn't hear.
Sorry for my English, but like how you will improve this project if you keep like if you want to keep working on this for the future?
Yeah. So as I mentioned in the speech, this project only focuses on one single robot, and collaboration robotic system is really essential in the search and rescue research. So if I can improve my project, if I have more time, I probably gonna like keep doing it, but like adding more robots into the tests to improve the collaborative robotic system for improving the efficiency of path planning.
Kind of piggybacking off the last question, is this project in particular something you look forward to as like a job for the future, like something you see yourself doing for the rest of your life, designing robots and rescue missions?
I would say probably maybe, but like I'm really into like the engineering and also like computer science stuff. But yeah, I'm probably gonna keep doing this project in the future and to see like if I can get more breakthroughs.
Yubo, I'm curious about whether you're also familiar with other algorithms that do similar things. I mean, I've got to assume that algorithms like this, you know, they're not just useful for search and rescue, right? They could be employed in war. That's a scary thing. But I'm assuming that algorithms that direct self-driving automobiles must also be similar. I'm just curious whether you're familiar with those and how similar those algorithms are.
So, like, yeah, as I mentioned in the speech, so the first traditional algorithm came out was the Dijkstra algorithm. It just created like a heuristic function to estimate the cost to the targets, and then like the researchers find out like there's another way to improve the efficiency, but still in the like one target to the other target. That was the A-star algorithm. So these two are like the traditional algorithms. And based on my test results, I found that they pretty like performs similar in both like path and time cost results. So yeah, so they are basically based on my testing.
I was just curious, when you were selecting where to place the targets in the maze, how did you determine that?
Okay, so there are like two phases for like the physical testing. The first stage is like the robot enter the maze and like scan the maze and create an initial 2D map. And so like I can see that initial 2D mapping on my laptop, and I can just like mark like the targets on the map, and I just put the map into the robot again, and the robot would re-enter the maze with the target added, and they will do the like path finding of it, like the missions.
You mentioned in your speech and like with your videos that your robot might not be the most practical in terms of real life situations, and I was thinking specifically with like debris and stuff in search and rescue missions. Would you stick with like a wheeled vehicle, or especially if you're doing cobots, or not cobots, multiple bots, would you think about more flight vehicles or robots?
Yeah, so due to the time limits, I only create like the easiest like the robot prototype, which is like the wheeled robot, and also I just created the like simple maze in the classroom. So it really lack of the complexity of the real disaster sets. But like in the future, so this algorithm not only like applies on the wheeled structure robots, it can definitely like be applied to any types of robots. So I'm assuming that I probably gonna keep doing this, and maybe I can build a more complex robot to let it to adapt to more complex environments.